Welcome. This is the Wednesday edition of this YouTube presentation for the Conceptual Physics class. And what we're going to do today is a little bit different in that instead of teaching you brand new information, I'm going to go through and do a couple of the problems on the assigned work together on this YouTube presentation. So if you watch and have your homework out as you're watching, you can actually answer some of the questions directly from the homework, and hopefully doing these few sample problems will answer the questions that you may have. So if you look under Google Classroom, your assignment due tomorrow, Thursday, March 26 at 11:59 p.m. is understanding the third law. All right, so we're going to start this. Understanding Newton's third law. The first question is simply, what is Newton's third law of motion? You've had several presentations and videos of that. It's pretty easy. If you don't remember, if you didn't write it in your notes, feel free to go reference the video that I posted on Monday. It's there. The next thing I want you to do is to watch this 3-minute YouTube video right here. The link is right here. It is an awesome video of people on the International Space Station doing Newton's laws experiments. They explain exactly what they're doing, and all I want you to do is to watch the video and explain why there is a difference in acceleration when the guy pushed the basketball and when the guy pushed the other astronaut. That's all I want you to do in that blank space. Okay, that's pretty self-explanatory. That's like a typical do now for our class. Let's get into the nitty-gritty. Action-reaction pairs. Oh, excuse me. Action-reaction pairs. This was explained in the Khan Academy last Thursday, but I feel like we need more of an explanation about it. Newton's third law says you cannot touch something without it touching you back. You cannot push something without it pushing you back. So if little Susie walks down the hallway and bumps into Nellie Newton, action-reaction. The general way I want you to think about this is if A pushes B, that's going to be the action. Then B pushes A. That's the reaction. Okay? The action-reaction pair is just that. It's a pair. It's only two objects. So action. For the first one, little Susie walks down the hallway, bumps into Nellie Newton. Action. Little Susie, and the verb I want you to use is pushes. Pushes Nellie Newton. Awesome. There's your action. So you see how it says A and B? A and B? In this case, A is little Susie, B is Nellie Newton. So if A pushes B, then just flip it. Reaction, Nellie Newton pushes little Susie. It's that simple. You are just writing sentences and figuring out what pushes what. In these first few questions, it's really obvious. Let's look at the second one. Little Susie walks along the floor. Action. Little Susie is the first object. Walks. What is the verb we're going to use? We're going to use the word pushes. Little Susie pushes the floor. Action. Reaction. The floor pushes little Susie. That's why she moves. If the floor did not push little Susie, she wouldn't go anywhere. This is why you cannot walk on ice. Ice has such low friction, it's not able to push you back. Or rather, you can walk on ice, but you can't really put your foot in an angle. It's almost as if you have to step straight up and down on the ice to kind of maximize your friction. At an angle, though, it cannot push you back. So little Susie pushes the floor, floor pushes little Susie. Simple. Can it get more complicated? Of course. Let's go ahead and do this. Nellie Newton talks a lot. Okay, if you're talking, technically, what is it that you're pushing? Good. Nellie Newton pushes the air. When you talk, your vocal cords vibrate and they push air out of your throat. If there's no air to push, there's no sound to make. This is why you cannot make sounds in outer space. If you're just floating in outer space and your vocal cords vibrate, there's nothing to push against. Therefore, you make no sound. The reaction is, of course, the air pushes Nellie Newton. Okay, that one was a little tricky. But let's see, let's keep going. We're gonna get the hang of this. Little Susie swims. Action. Little Susie, the verb we always use is pushes. Okay, when she swims, what's the other object? The water. Good. If you swim, rather, when you swim, you can't go forward unless you push some water backwards. You cannot do it. If you think about the strokes that you use, you kick your feet back, you're pushing water back, you push your hands back. By pushing that water back, then what that does is the water pushes little Susie forward. Action, reaction. Okay. Good. So those are the first few. That's how you do those action-reaction problems. I will let you figure out the rest of them, but I'm going to jump right to number 11. A ball falls to the ground. This one's tough. We talked about this a little bit in the other presentation, but let's really get into it now. A ball falls to the ground. What are the two objects? We have the ball, and what's pushing the ball? A lot of people are going to say, oh, well, gravity's pulling it or pushing it down. That's true. But is gravity an object? No. Gravity comes from where? Planet Earth. So the second object is the Earth. So as a ball falls to the ground, action. Earth pushes the ball to the ground. And then the reaction is that the ball pushes the Earth back or pulls the Earth back. So wait a minute. If the forces are equal and opposite, because the Earth has so much mass, the little force that moves the ball is nowhere even close to being enough force to actually move the Earth. So even though the Earth and the ball are pulling on each other with equal forces, only the ball moves because the ball has such a smaller mass than the Earth. The Earth is not going to move because the ball is pushing on it. It just has too much mass. So let's look at this example. Here's another question on your homework. A minivan is driving down the road and hits someone riding a bike. An unfortunate situation. Which one experiences more force, the biker or the minivan? Technically, they experience equal force. They experience equal or the same force. According to Newton's third law, you cannot hit something harder than it can hit you back. You have to hit with an equal and opposite reaction. But the problem is, the reason why the biker gets hurt in this situation, and chances are the minivan, the people in the minivan are fine, is that which one has more mass? Because the minivan has more mass, it will have less acceleration. So when it says which one experiences more acceleration, that's going to be the biker. And that added acceleration to the biker is going to introduce all the problems and injuries that is likely to happen in this situation. So they experience the same force, but I want you to understand that the same force is going to have different results on different objects. Same force, but not the same result. That's the key behind Newton's third law. Action, reaction. Okay, so questions 1, 2, and 3 on the math section, we did exactly on Monday. Those were done in that video. If you forgot how to do that, please reference that video. Questions 4 and 5 on the math section, however, are just a little bit different. Not crazy different, just a little different. Now, it says you may need to use one or more of the equations above to solve these last questions. Oh, whoops, grammar. My bad. Sorry about that. These last questions. Okay. Little Susie and Nellie Newton are both standing still next to each other. So, all right, we're going to do this. There's Susie. There's Nellie. There they are. Awesome. They're going to have this. I'm drawing the same picture that I drew for the other problems. I'm going to go ahead and draw the acceleration and the mass. There's Susie's hair. Okay. Acceleration and the mass. Yes. So what are we going to do here? We are going to, it says little Susie has a mass of 39. So 39. This is little Susie, of course. All right. And Nellie Newton has a mass of 61. Awesome. If Nellie Newton accelerates plus 2.1, all right, I remember how to do this. In order to get Susie's acceleration, we need to get the force. So we get the force by doing the FEMA triangle. Yes, let's FEMA that. I like that F. I drew that F very nicely. Okay. 2.1 times 61 is, of course, 128.1 newtons. And if that's 128.1, this is 128.1 newtons. So to get the acceleration, I'm going to FEMA that again. All right, F, M, A. All right. Okay. So I'm going to do 128.1 divided by 39, and I'm going to get an acceleration of negative, why is it negative? Because it's going to the left, 3.28 meters per second squared. Am I done? Well, I got her acceleration. So this is what you do. You do the first part of the problem just like we did before. Now we're going to add another step. It says, assuming the push lasted for 2.6 seconds, how fast is little Susie moving? Okay, how fast? That's velocity. So we're looking for velocity. Velocity equals question mark. All right. Her acceleration for little Susie is negative 3.28. We just solved that. The time is 2.6 seconds. It's given. Good, 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 good. And because it says they were standing still, that means the initial velocity, or the V naught, is 0. So what you're going to do is you're going to look at the three kinematic equations, 1, 2, 3, and now that you got the acceleration, you're going to use one of them to solve for it. Go ahead. You're either going to use equation 1, 2, or 3 to solve for the velocity. Once you get the velocity, that's your final answer. Question 5 works similarly, in which you will set it up like a normal problem, and then you will use their accelerations in these kinematic equations. Thoughts, problems, questions, concerns, anything you guys need, I'm here. A lot of people have emailed me. I will get back to you as soon as I can. Good luck. You got this. And this is Newton's third law. This is pretty much everything I want to do with it. So we are learning this even though we are not in school. It's like we're in school, but different. Guys, be well, and I will see you all later.